Dear learners, let us analyze one more continuous beam by slope deflection method, and this is also a indeterminate structure, and the degrees of freedom is going to be 2. How it is going to be 2? Theta A 0, there is fixity, so rotation displacement is not possible. At end B, theta B is possible, rotation will occur, and end C, theta C might come. So there are 2 degrees of freedom, theta B and theta C. And this beam is in first span AB. It is subjected to a concentrated load 100 kilonewton acting at a distance of 4 meter from the left end, and total length of the span AB is 6 meter, and span BC is completely loaded with UDL, and the span length is 5 meter. So the unknown in this unknown displacement in for this particular beam is theta B comma theta C. Theta A is not it is not available, and theta A can be considered as 0. So we have to work out all the fixed end moments, and let us consider each beam ends to be fixity at both ends. So AB, span AB, you can see 100 kilonewton load at a distance of 4 meter, and 2 meter B, 4 meter A, and B 2 meter. And this fixed moment FAB is minus WAB square by L square. So if you substitute A comma B, the values are minus 44. FBA WA square B by L square. WA is 4 meter 4 square, and B 2 meter by L square. So minus 44 FFAB and FBA plus 89 kilonewton 88 kilonewton meter. And next span FBC, it is completely with UDL, full UDL acting over the entire span. So minus WL square by 12 left side, and right side moment plus WL square by 12. So if you substitute W 20 kilonewton meter, you can get span length 5 meter. So left side fixed moment FBC is minus 41 and FCB plus 41. So after finding this bending moment, we can write the slope deflection equation. And before that, we decided already theta A is 0, and theta B and theta C are the unknowns. So with this, we are writing the slope deflection equations. MAB equal to fixed end moment followed by end moments. So fixed moment FAB plus followed by 2A by L, 2 theta A and theta B. Theta A is near end in MAB, and theta B is far end. So substitute 2 times theta A for near end and theta B for far end. And you can cancel theta A. So the next moment becomes minus 44.44 plus 1 by 3 EI theta B. Equation 1 is ready. Now equation 2, MBA FBA plus equal to FBA plus 2A by L, 2 theta B plus theta A. Now theta B is near end and A is far end. And you can remove theta A, and remaining terms is substitute. So 88.89 plus 2 by 3 EI theta B. So after that, one more span, BC span is there. So we have to find the moments MBC. So again, the fixed moment FBC plus 2A by L, 2 theta B plus theta C. So you substitute 41.67 and 2A by L, 2 theta B plus theta C. Next 41 point minus, simplify this, 41 minus 41.67 plus 4 by I 5 EI theta B, 2 by 5 EI theta C. So this is the third equation. Similarly, on the other side of this span, MCB equal to fixed moment plus 2A by L, 2 theta C plus theta B. Again, you write all the values, plus 41.672 EA by L, 2 theta C theta B, and you simplify this, you can get equation number 4. So there are 4 equations and 2 unknowns, theta B and theta C. And now we have to think about the conditions to solve the 2 unknowns. So what we can do is at joint B, intermediate joint, we can take sum of the moments meeting at the joint equal to 0. So if you're taking joint B, this side MBA plus MBC equal to 0. This is one condition, and we need one more condition. So you can observe the extreme end is simply supported. So the moment MCB is going to be 0. So using these two conditions, you substitute MBA plus you add MBC and simplify, you can get equation number 4. Okay. So similarly, you equate MCB equal to 0. So using this equation 5 and 4, 6, you can solve what is theta B and what is theta C. Theta B is minus 20.83 by EI and theta C is minus 41.67 by EI. Negative sign indicates rotation is anti-clockwise. So after getting this theta B, theta C, we can move forward to finding the end moments. So MAB equal to, so we can recall the equation number 1 and we can substitute minus 44.4 plus 1 by 3. EIA gets cancelled, theta B is substituted, and finally we are getting the moment minus 51.38 kilonewton meter. So MBA, similarly you substitute theta B, theta C values, you can get plus 75 kilonewton meter. This is the final moment. And similarly for the next span MBC, we have got minus 75 kilonewton meter. MCB already we know it is a SS end, simply supported end. So moment 0. So this diagram clearly shows the final moments acting at the beam ends. So MAB we have taken minus 51.38, MBA plus 75, and this is minus 75 and this is 0. So this diagram is important. Now once we know all the moments, we can draw the free body diagram and find the reactions and shear force, bending moment, etc. So let us consider each beam span by span. Now the problem becomes statically determinate. So now you consider span AB, you keep all the external loading, end moments. So now we are in position to find RA and RB1. RB1, just considering span AB, you find RA and RB1. So RA 70.60, RB RA 29.40 and RB 170.60. Similarly, you take the next span, you keep all the moments, external loading, and find RB2 and RC. Simply by using the static equilibrium conditions, we can achieve all the supports at the reaction support. Then you plot the bending moment. Um, Using this data, we can plot. So this moment is F51 and this moment is 75 already we got, and this is 0. And next you can see the triangular variation. So this is for span moment. So some unequal, not an unequal distance load, you can see concentrated load. So WAB by L formula is substituted. We have got 46.232 and this is 30.662 for W for this span with UDL. So if you overlap the span moment and end moment, we can get the net bending moment diagram. Similarly, with the reactions have obtained from the static equilibrium conditions, we can plot the shear force diagrams. Thank you. And this is the maximum bending moment. Since bending moment values are to be estimated at the salient points, so we have calculated the bending moment in the Mmax, that is going to be 46.2, and in span BC also we calculated the maximum bending moment that as 30.62 kilonewton meter.